Hello everyone and good afternoon. Welcome back to the Shure Masterclass Wireless Best Practice and Techniques. We are at episode 3 today and we'll be talking about signal processing and in-ear monitors. A little bit of housekeeping. You have a very comprehensive section of tools at the right of your screen. There is a chat. There is the possibility to answer to some questions that will be thrown to you during the webinar, and there is a Q&A section, where you can for clarification or more topics to be covered or whatever you need to know about what we are discussing today. I hope my audio is good, you can listen to me clearly, and we are ready to start with signal processing. We saw in the past episode analog and digital RF transmission, so we have been focusing quite a lot on how we put together the data to be transmitted from one point to another. And today we will be talking about what happens to our audio signal a little more. The very first problem in transmission of our RF can be the noise. And over the years, technology evolved and we had several ways to prevent the noise to enter our audio path. Obviously, as you can see from the picture on your screen, the analog transmission is the most affected by noise. And it's been also the first technology to be deployed. So we went from analog amplitude modulation to frequency modulation to reduce the noise, but a part of it was still there. As you may know, probably, the high frequencies are more susceptible to noise than the low frequencies. Therefore, very soon, very early, it's been introduced an emphasis equalization to help the noise, to help us to avoid noise. The second step was about dynamic range that had to be controlled somehow, and therefore we have a companion system. This can happen in an analog processing or with digital processing. Even though we have analog RF, an analog signal to be transferred from point A to point B, the digital processing happens in the hybrid type of RF transmitters and receivers that sit in between the complete analog and the complete digital system. So let's start with the emphasis. Most of the time, we at the transmitter side decide to apply a transparent EQ that is a boost about 18 dB, usually sometimes 21 over 1 kilohertz. This is happening to like it used to happen for tape machine with Dolby processors. At the receiver stage, we reverse the process and we apply an inverse EQ that is reducing the high frequencies by 18 or 21 dB. The overall result is that we have linear audio, but the high frequencies traveling over RF have been traveling very much boosted. They eventually can catch some noise, but then there is a 21 dB reduction that will reduce the noise accordingly. The second part of a signal process, mostly in the analog domain, is about the dynamic range. As we saw in the previous episode, the dynamic range of a signal is limited by the deviation of the RF signal. That is 200 kilohertz by low. This means that we can have about 50 dB of dynamic range. Therefore, we need at the transmitter stage to apply a compressor, have compressed signal to travel over the air, and then an expander at the receiver stage will bring the signal back to normal. What we need to consider here is that making these processes exactly the same at the transmitter and receiver stage involves the tolerance of components. The more component has tolerance, the cheaper it is, and vice versa. This is why we can confidently say that top tier and more expensive systems can sound better than others in the analog domain. Other than that, after this process that regards audio, we have as well an RF processing. So we pack our signal, we make the audio signal as we like to be transmitted, and then we actually have to transmit. And after the receiving antenna, we have as well to do the reverse process. So let's see how this happens in the analog domain. So first of all, as we said, we have a preamplifier. In some of the analog devices, we have control on this preamplifier. Then we have an emphasis EQ that is giving a boost at the high frequencies. Then we have a compressor. Of course, we have different type of compressions, and we may see more in details how they work at a later stage. After that, we have the radio part. Our signal is going through a VCO controlled by in frequency and phase by an oscillator, and therefore goes to an RF amplifier that finally brings the signal to the antenna. The receiver setup is a little more complicated because we have two steps. We have a front-end filter that discriminates what our receiver can actually see. Then we have a mixer where we mix the input from the antenna together with an oscillator that brings the frequency back to an intermediate frequency and then gets demodulated from this intermediate frequency that typically is 10.7 megahertz. Why this is important to remember that we have an intermediate frequency, like as our everyday users, we may even ignore this intermediate step, but we need to remember that this is again a kind of a source of RF. So we have an oscillator inside the box that's interacting with other oscillators in the box on top of each other. So this can as well create some intermodulation in the receivers. And this is something, intermodulation is something that we will discuss more in details during the next episode of this training. And then on the audio side, we have the expander and the reverse emphasis EQ before we go to an amplifier, and then we can finally get out of our box with an audio signal. So the down conversion to 10.7 megahertz means that we may produce harmonics due to nonlinear design of the components, and therefore we may find ourselves producing intermodulation at the receiver stage too. A few words on the front-end filter that we have already been discussing a little in the past episode. This is the very first line of defense for our receiver against interferences. So we want our filter to be as selective as possible. And luckily, It's not like probably audio, where we can be over selective and we can have very efficient brick wall filters up to, I don't know, 48 or even 100 dB per octave. Here, things are working slightly different. So the shape of a filter, as you can see from the picture, is not a brick wall at all. And this is having an effect on how we work with it and how filters are built. What we can see very easily and without going into the filter technology itself is that we have two types of filters. One is a fixed filter and one changes according to the frequency that we select. But the wider the filter is, the wider the filter can be tuned. So if we have a wide tuning range, our filter will not be as selective as for a narrow band filter. Meaning if my device is capable of tuning in a range of 20 megahertz, I can have a pretty selective track tuning filter. But if my device is a wideband device, like 150 megahertz, my selectivity won't be that efficient, and I cannot have track tuning filter like with a span of 15 or 20 megahertz capable of tuning in a wide range. This is why there is for the analog systems, there is always a certain compromise to be taken between selectivity on one side of a filter itself and tuning range of the device. In the digital domain, these things are working slightly different because we have, after this first line of defense, we can work with digital filtering, and this helps to have wideband receiver with kind of very selective filters too. Another portion of another feature of our receivers is the squelch. For who already attended one of these trainings, you may have heard this story before, but I remember the first time I had to deal with an RF receiver. I connected my mic, I put PFL on the mixer, and I started talking in the mic, moving the squelch, and nothing happened. So I thought the squelch was pretty much useless because it wasn't changing anything. But the squelch is a very important tool and feature. So let's see how it works, because yes, it's not gonna change our audio output. What squelch is doing is behaving like a gate. So a gate in the audio domain opens when we have enough signal. The same is happening with the squelch, but the side chain is not the signal itself, it's the amount of RF that we have. Over the time, squelch have been refined, and we found different types of squelch that can help us better than just quantity squelch. So it's not just quantity, it's the squelch evolved and now can be controlled by, in example, the amount of noise that is entering the device. So if my device recognizes that there is more noise than actual signal, and how we discriminate the noise? By the quantity of high frequency and the quality of high frequency. So depending on how much noise we have, the squelch can open, meaning letting the signal go, or keep or stay closed. Other than that, we have also the noise squelch that is mostly, or at least partly, in use in in-ear monitor systems. We'll discuss about in-ear monitor specific squelch later on. The most common for professional wireless is the tone key squelch. The tone key squelch is a tone, 32 kilohertz usually, Most of the time, that's different from model to model and from manufacturer to manufacturer. This is why I cannot connect the LX transmitter on an SLX receiver or vice versa, because they have a different tone key squelch. This special tone is out of the audio bandwidth, and together with the green light for the squelch to open carries some additional information that, depending on the model and manufacturer, can be different. Most of them can carry battery level information. Some of them can carry information about the transmitter, so power level, audio gain settings, lock settings, or even other different information. If this tone is recognized, then the squelch will open and audio will flow. If this tone is not recognized, then the squelch will close the gate and you will have no audio at the output. This tone key squelch, that in Sennheiser world is called pilot tone, but technologically is exactly the same thing, will give us some other additional benefits. Now imagine that you switch on and off your transmitter. This will create noise because you will have a signal that will be interrupted kind of in a very brutal way, creating a noise at your receiver. The squelch assists the on-off procedures. So when I switch on my UHFR transmitter, an example, I have the tone key going live first, and then when the tone key is received, audio flows. This is preventing noises, unwanted noises, when we switch on and off the devices. In the digital domain, this is realized slightly different. So what we have, that we recognize that the bit error rate is low enough to have good quality signal, and then we can open our gate. But ideally, the concept doesn't change. So the squelch helps you to have a silent operation of switching on and off, as much as it helps you to prevent noises. In example, the pure RF noise, when we switch off a transmitter, we would have pure RF noise decoded and sent to the audio output. The squelch interrupts the signal and makes sure that your audio output, when your transmitter is off, will be muted. I see that we have some questions live here. A smaller antenna is suitable for higher frequency, and longer antennas are required for lower frequencies. I hope you answer, guys, and you answer correctly, because I see some weird result here. Okay, moving on. I see another poll gone live now. After the squelch, if we are talking again about signal processing, and we focus again on our RF signal, what's next is basically the explanation of why our receivers, most of our receivers, are having two antennas. The answer is relatively simple, and I want to be extremely clear with you. I said it in the beginning of a training. We sometimes, to explain a concept, we want to make it more simple. So this is one of these cases. So bear with me for a second. In audio, you know very well that if you have two signals, one is perfectly in phase and the other one is exactly with opposite polarity, so completely out of phase, 100 degree rotated, and the two signals are equal, the result will be silence. The same thing may happen with multipath interferences for RF. Now, where is the simplification here is that if we use a single antenna receiver and we go around in a room looking for the spot where we have a perfect multipath interference perfectly out of phase, we are not going to find it. So by itself, a multipath interference would not produce a dropout, but the dropout is always a consequence of multiple things going wrong. So multipath interference can be one of them, and we can prevent it. So you can see the animation is not, yes, you can see how changing the transmitter movement changes the quantity of signal that reaches the two antennas, and how eventually there is a cancellation related to this multipath interference. To be completely open with you, we also have some anti-echo filtering inside the most advanced receivers. So this is something as well that you can take into consideration that will help you preventing a complete dropout due to reflections. But still, as you saw in the graphic, that was pretty accurate. You can see a reduction of the quantity of signal reaching your antennas. That's pretty significant. So the first way to react to this multipath interference is to place two antennas at the receiver, have a pure and simple passive combiner, and then having this combined signal go into a receiver. But it has a plus, it's very simple, easy, and cheap, but it has a couple of minus. One is that you're technically building an antenna array, meaning that the directivity of your antenna will be affected by the interaction of antenna A and antenna B. Plus, you don't have any control on it, and antenna B can actually subtract some good signal from antenna A. So this is the very first step into what is diversity. Diversity means having two antennas somehow under your control to prevent multipath interference. Another simple system that is used in some old analog systems as much as in some digital systems, because it's very efficient for digital, not as efficient for audio, is predictive antenna switching. So as you can see in the schematic, you have a switch between antenna A and antenna B that's controlled by a predictive comparator that receives information from the receiver itself. So by default, I'm working with antenna A. The receiver receives minus 20 dBm, so super loud signal. He's happy, it doesn't change. But then this signal starts to go down. Let's say that it goes down up to minus 60, 50 dBm. At this point, the predictive comparator knows that signal is going down, therefore switches to antenna B. It's functional, but the minus of this system is that we don't really know what's happening on antenna B. Situation may be even worse, and then we have to go back to antenna A without knowing what happened in the meanwhile to antenna A. So the predictive comparator, it's a good system under certain conditions. One of them is having a RF spectrum that is not too noisy, because this can confuse a little bit the comparator. And obviously, it doesn't work very well at the edge of the capability of a system. After this, we have receiver switching diversity. This is not really in use with in any Shure device, but it's pretty common in some third-party high-tier devices. What happens? We have two antennas going to two receivers that transform and do all the process for you, transforming the RF energy into audio. And then the audio is switched between A and B, usually comparing the quantity of noise into the audio. In the old days, this type of diversity was having some issues related to the noise of the switch, but in recent years we didn't see this problem happening anymore, and this is a kind of efficient system. But quite some time ago, we thought we could improve this system, and how we did it. Having a system that was called MARCAT, that stands for Maximum Ratio Combining Audio Diversity. So the process is exactly the same. We have two antennas input, two complete blocks of receivers that will give two audio signals feeding a combiner. If both signals are good, what we get is a 3 dB increase in signal-to-noise ratio at the audio level. And this is a pretty good result. How the combiner is working, imagine a pen pot in reverse. So you have two input and a single output, and the system goes towards one or another antenna depending on which of the two is performing better. Now, if I don't have problems with my presentation, we can move to something different. This process was happening in the analog domain. In the digital domain, we have something called true digital diversity. Substantially, it's the same process, the same blocks, just working with a digital signal. To explain true digital diversity, that is the type of diversity used in accent digital, we need to have a couple of extra information. One of them is about the signal we are broadcasting. Accent digital, together with the digital world, having audio and packed in a certain way inside what we said is a codec. After this process, there is a kind of print mark given by the transmitter. You can look at it as a kind of MAC address, unique stamp given by every and each transmitter. The receiver will read this pattern of bits and will be capable of understanding the signal to noise ratio better, the carrier to noise ratio at an RF level. So if out of 32 bits of this print mark I receive only 8, my signal, my transmission is very much disturbed. If I receive 32 out of 32, it means I'm working in ideal condition. Everything is very good. The second piece of information that we need to fully understand the digital diversity is about what happens next. Now, you may know that there is no digital transport that allows 100% of data package transmitted and received perfectly, on time, correctly, without any loss. For who of you attended yesterday, there was a very interesting conversation that I had with Gus from Odinate. We have been talking a lot about digital packets and how we transmit digital signals over network. And even there, even over a cable, there is a certain amount of errors happening. This is called bit error rate. For this, there is an error correction code. That means that the system is doing some calculations mostly at mathematical level, to correct the errors due to transmission and reception. All of this can take time. Then we come to true digital diversity. How true digital diversity implement this combining thing that I remind you is working somehow like this. It's having two RF lines transforming the signal up to the level of digital audio. So a stream of bits 0 and 1. Two things are taken into consideration. How the packets are reaching the receiver in the right order, and how many bits out of this pattern are recognizable into the two data streams. With this in mind, with the perfect clocking, I won't go into details about how it's working inside the receiver, but with the perfect clocking inside an Axiom digital box receiver, we can put together the information coming from both antennas. And this is giving us a great advantage because we can extend the coverage area, or we can even work with the antennas in a very different way. So here, what you are seeing is on top a timeline of wireless workbench, the two antennas, and down what we see are the two raw signals that then are put together going through the error correction code. Why it's important to have a sum before the error correction code? Because in this way the error correction code doesn't require much calculation and keeps the overall latency of our system very, very low. But because of these capabilities, we can do something different and kind of special with and unique with an Axiom digital receiver. That is called quad Versity. With quad Versity, 4-channel receivers, that means a machine that has 8 RF blocks, instead of having 4 channels, can become a 2-channel receiver, but every channel has 4 blocks of RF, transforming RF into audio. How does this work? If you look at the back of a quad receiver of Axiom Digital, you may see that there are 2 antenna inputs and then a cascade output. This cascade output is repurposed into an additional input. So you feed your box with 4 signals coming from 4 different antennas. At this point, your device is a quad receiver only by name because it's actually a 2-channel quad Versity receiver, having for each channel 4 antennas feeding it. Why this is related to the digital diversity we discussed before? This is related to it because it's the capability of independent process of each antenna that helps us to realize quad Versity in a receiver. So with 4 signals, we can work in different ways. A common way might be to extend the capability of a system in terms of coverage area. A small example, during Easter concert, Andrea Bocelli performed in Duomo in Milan, and he was having actually 2 stages, 2 places where he was singing. He was having his Axiom digital transmitter on him, and he was the first set was he was singing. During the first set, he was singing inside the cathedral, and for the second one, he was just outside the door. So of course, one possibility was to put multiple receivers tuned in the same frequency, but this was not a very efficient way to operate. Plus, he may have the signal that was captured outside the cathedral might have been useful also for the set inside. So quad Versity was in place, 2 antennas inside and 2 antennas outside, covering technically 2 different RF area and extending the coverage up to 150 meters, with the additional benefit that the output was always on the same audio channel. So no need for double receivers, double channels on the mixer, double everything. It was always the same channel with the same processing method, with absolutely the same sound going for a very big area. Another way to use quad Versity is the example is, I think it's Taylor Swift concert that I saw recently. They were using quad Versity. The problem there was a very high noise floor due to the multiple LED screens that were around. When you have a very high noise floor, all you can do is to keep your antennas as close as possible. And with quad Versity, instead of having just 2 antennas, mostly on the side of a stage or even on the center of a stage, they add distributed antenna every 12 meters on stage, covering a complete 50 by 100 meters area with absolute peace of mind. So having 4 antennas instead of 2 is a major benefit. Using quad Versity instead of a simple combiner that I may decide to go in a different direction. I don't have quad Versity, but I need to cover 2 areas. What I do, I place antenna A and antenna B, let's say outside the church, antenna C and antenna D inside the church. I bring the cable and then I simply passively combine antenna A and antenna C, antenna B and antenna D to my diversity receiver. In this way, I can cover 2 areas, but I sum up the noise from outside with the noise from inside. And in a modern environment, this can be extremely challenging. Therefore, quad Versity is another weapon that you can use to fight against RF noise and leak of coverage or need for extreme coverage, and the applications are countless. When Accent Digital was launched some years ago, I saw a very nice video that was recorded in Chicago Stadium. And I thought, oh, it's very cool, but is it really having a use in everyday life? But after 2 years, I can really tell you that quad Versity is a very important feature, and you can really benefit of it because yes, it comes with a cost. The quad receiver becomes a dual receiver, but the quality of your signal increases drastically, and the amount of options that you can cover with a single receiver and 4 antennas instead of 2 is really impressive. You can be always very close to your antenna, and the system will use only the good signal with discarding all the unwanted noise. So if you see a system, how a system behaves with 4 antennas and a passive combiner compared to quad Versity, you can really feel by yourself the difference in terms of security and peace of mind for your signal. If you have any additional question about diversity, technology, and what happens to your antennas after they enter in the box, please use the Q&A section. If not, if you have questions about antennas and cables and antenna placement and RF coordination, then you have to be a little more patient because these topics will be covered in the next 2 sessions. Because of a heat break, we won't have a session next week, so we will start over with this masterclass in 2 weeks from now. I said in the beginning that signal processing wasn't the only topic of the day, and actually it's not. The other big chunk of a training today is in-ear monitors. The first question that comes to my mind talking about in-ear monitors is that are they the same as radio mics, just working in the opposite direction? But of course, they are not. Why they are not? Because when we broadcast in-ear monitors, when we broadcast a signal for in-ear monitors, we broadcast most of the time a stereo signal. With PSM 900 and 1000, we have also some other options, additional options other than stereo. I just want to mention one, that is mixed mode. In mixed mode, you can send, instead of left and right signal, you can plug A and B signals. This can be completely unrelated. One can be a voice, and the second one can be a background music or a program or whatever you can imagine. Two unrelated signals go in the same transmitter to the same receiver, and then at the receiver stage, you may decide how much of signal A and how much of signal B you want in your earphone. But before we dig into the RF part, I'd like to spend some words about the most common accessories that are going together with in-ear monitors. So this part is about earphones. We can connect almost every earphone to our in-ear monitors, but not all of them will answer in the same way. And this is related to the impedance of the earphone itself. Earphones and headphones too. Nobody is telling me that I cannot connect my 1540 or even better, somehow my 1840 audiophile headphone to an in-ear monitor packet. I can, but the result won't always be the same in terms of volume. So the volume that we can have out of an amplifier is always related, as it happens for the speakers, to the input impedance of the other device that is connected to the amplifier. In this case, we are talking about earphones. Impedance value is what gives us more or less volume out of the earphones. Here I have three models of earphones with three different impedance levels. SE425, that for who's curious is my earphone of choice, is having 22 ohm of impedance. That is not as low as SE846 that are having 9 ohm of impedance. They would be my earphone of choice, but they are just probably too expensive for me. UAE Live, that is a very popular, maybe a few years ago it was even more popular, model of earphones made by Ultimate Ears, is around 10 ohms. This level, let's say around 10 ohms, is typically the level of the custom in-ears. So they are offering the best performances. They are usually sounding very nicely, as much as the SE846. When we see the impedance level going up, then we have a little less volume. Personally, I'm not a singer. I don't need my earphones to perform on stage. So 22 ohms is, in my opinion, the perfect balance for a sound engineer between quality and volume. If we need to have more volume, that means lighter components and keeping the same quality or even increasing the quality, then we probably need to spend some more money. Average level for very efficient headphones is 25 to 50 ohms, but audiophile headphones can go much higher in impedance, reducing the volume sensation that you get out of your headphones. So this is the first thing I wanted to tell you. Why is this related to RF? Yes, it is. Why is this related to RF? Because whenever we deal with in-ear monitors, specifically with very powerful in-ear monitors like the PSM 1000 that you see in the picture, my recommendation to have the best sound together with the best RF signal is to keep the input not too hot. Why I'm saying so, and why is this related to the RF transmission? We'll see it very, very soon. Just to remind you one thing, what you see in the meter of any device is most likely affected by a sort of averaging that happens. So the meter may not show you completely the peaks that are happening because the transient may be too fast. So the meter is for you an indication of average energy, but might not represent completely the peaks that a very dynamic mix can have. And typically, a band playing live has much more dynamic than a CD. Why I'm putting all this information in front of an RF explanation? Because you can see on your screen now how the thing is built. What we transmit with in-ear monitor is the way we transmit stereo is happening because we use a technology that was FCC approved and established in 1961. That's called stereo multiplex transmission. Stereo multiplex transmissions as gather with the package, and it's exactly the same for any stereo in your monitor in the world, a limitation in terms of frequency response. Frequency response of multiplex stereo to be approved by FCC, so to be legally sold, has to be limited between 50 Hz and 15 kHz. This has a lot of implication for us, especially for monitor engineers. I mean, I was a monitor engineer so long ago that I don't think I belong to the category anymore. But this has a lot of implication. Plus, if you look at the picture in the center, you will notice that there is a line at 19 kHz. This is nothing else than a tone key that is informing the receiver that is getting a stereo transmission. Stereo transmission, and from 23 kHz to 38 kHz, we have the second part of a signal. Now, you may wonder why they didn't decide to put left from 50 Hz to 15 kHz and right from 23 kHz to 38 kHz. Reason is that this wouldn't be monocompatible. So what happens is that to get monocompatibility, what we do is putting together left and right, or in the case of mixed mode, even two unrelated signals that are A plus B, and in the second portion of spectrum, so with a frequency shift, we can have the difference left minus right. Restoring the stereo image will give us a benefit in terms of dynamic range and signal to noise ratio. The only limitation is the frequency band in terms of audio. So we lose anything. There is a brick wall filter at 15K, means that we lose all the super high frequency. Now what happens? We may be tempted of, oh, the singer doesn't hear enough very high frequencies from cymbals or from a violin or whatever. We may be tempted to boost that signal. Nothing can be more wrong, because what we would do is we would confuse the receiver, boosting the high frequencies, we may have some problems. We may create some problems at the brick wall filter and eventually at the tone key. Result would be a stereo image that will be collapsing. This is why on most of in-ear monitor systems, you may find an EQ like high frequency boost or things like this. In this case, it's much better to boost the high frequencies at the receiver stage than at the transmitter. I just want to spend a few more words about P10r Plus, because with the new receivers for PSM, we made the next step into in-ear monitor, and we included a lot of digital technology into an analog system. If I received the question several times, so I hope I'm anticipating someone, why there is not a completely digital in-ear monitor system. The answer is because there is not a digital multiplex technology that allows a latency that is low enough. So for the time being, I don't know if it will be like this forever, but definitely for the time being, all the high profile, expensive and good sounding in-ear monitors of the world are broadcasting an analog signal. But with P10r Plus, we are benefiting of digital technology inside the transmitter and the receiver too. Before, it was only at the transmitter level. So as you can see, we have an input stage where we have a preamp that is managing our signal. Then we have a DSP where we can perform different operations. That is digital. Then we go to multiplex modulation, FM modulation, and then we broadcast the signal. In reverse, at the receiver, we have RF input that is including diversity, because most of you probably knows we have two antennas in a PSM 1000 receiver. Then the FPGA chip is taking care of FM demodulation, multiplex demodulation, a DSP that is changing the signal, so you can have an EQ, you can have a boost in high frequency, or technically with P10r Plus you can have a 4-band completely open EQ, parametric EQ, and then we have the headphone amplifier. This integration of digital and analog, it's for the time being the state of the art in regards of in-ear monitor. How it's gonna be in the future, I don't know. I can guess that at some point we will have a digital multiplex modulation system approved by FCC that will work enough for our in-ear monitors, but for the time being, this is definitely the state of the art, and it's the best compromise we can have between stereo transmission, audio quality, and the reliability that is absolutely increased because of the use of an FPGA. So I hope I confused you enough. So I'm ready to answer your questions if you have any. Just before it, I'd like to remind you that next session of the wireless masterclass will be in 2 weeks from now. Most likely you should receive an email from our very hard-working marketing department. So we will keep you posted about probably some other initiatives that we will have during this time, most likely after a break, and about the new episode of the Wireless Masterclass. Oh, I see on the chat Samir saying no summation, either A or B, but he said so 29 minutes ago. So Samir, honestly speaking, I don't know what you are referring to. If you want me to clarify some point, more than happy, but please let me know. Then I have another question asked by Peter. Thank you for your question, Peter. The question is, can we have few channels with quad versity whilst others and standard dual diversity? Yes, of course, the two systems can coexist. The only limitation you have to deal with is that you cannot do it in the same box. So once you transform your box into a quad versity receiver, that device, that physical rack unit, is two channels in quad versity. But of course, in a system, let's imagine we have a band and the singer that loves to run on this ego ramp towards the audience. You may have the whole band in a standard diversity and the singer, maybe with a backup mic always ready, in quad versity. So you can mix and match and decide to have only certain systems in quad versity and other in normal diversity, but not in the same box. The other question that I read comes from Ranjan. Hello, Ranjan. Does running in-ear monitors in mono give you more transmitter power? If you are talking about coverage area, I'd say no. There is not an extension of the area you can cover. And I'd say also, like, if you set up, let's say, a PSM 1000 in mono, the receiver, at the receiver level, what happens is that it's broadcasting on both sides of a multiplex mono signal, then goes back and sum up left plus left or signal A plus signal A to boost the usual 3 dB in signal to noise ratio, but you don't have additional power or, as far as I'm concerned, any other benefit using linear monitors in mono versus stereo. Ramon saying it's clear, very good. Last but not least, the polls. So I see some of you is interested in a Q&A session. Most likely we will have a comprehensive Q&A session just after the last episode of a wireless masterclass, maybe the next day. So you can clarify yourself before taking the actual exam if you're planning to do it. Then let me go through the polls. How is the frequency of a radio wave measured? Cycles per second. Of course, most of you got it right. Very strange. I don't know how many people answered to this question, but a smaller antenna is suitable for higher frequency than a longer antenna. Everybody answered false, but it's true, guys. The dimension of accessories is very much related to the dimension of a wavelength. Smaller antenna, higher frequency, smaller wavelength are in the same package. Just to clarify the point, you can go online and look at the dimension of a VHF antenna from Shure, or comes to my mind the radioactive design intercom system that has a very similar and very big VHF antenna. So the higher the frequency, the smaller the accessories will be. Let me go back to the question. Christoph, does it make sense to use helix antenna close to stage? Very good question. I do not have a specific answer. There are the antenna, like, yes, sometimes, some other times not. We will discuss more in details when we will talk specifically about antennas. So in 2 weeks, we will have an episode about RF coordination basics. I know that some of you attended already the wireless workbench training, so we will cover somehow the same topics, but from a different point of view. Why we need to coordinate, what are the phenomena that we can take under control with wireless workbench from a physical point of view, what happens, what's creating interference, how these interference are looking like. So I invite you to resist another 2-3 weeks, and hopefully we can have. I think that antennas coverage is more a topic for discussion than for a teaching topic. Like there are so many factors to be taken in consideration that the selection of the antenna type can be really depending on your need and on your specific situation. One of the guys who attended, I'm sure, the wireless workbench seminar is Ranjan, who's asking, so you get a higher signal to noise ratio with mono? Absolutely not, because the 3 dB in signal to noise ratio, it's something you get also on a stereo. So no, the signal to noise ratio is somehow the same. Peter is asking a very interesting question. And I know we exceeded the 1 hour time, so resist a little. Is it possible to simulate RF behavior in a room similar to a Wi-Fi heat map? Does Shure have any tools such as this? More than a Wi-Fi heat map, what comes to my mind is smart or easy acoustic simulation software. By the way, the answer is no. Why? Because the mathematical model would be so complicated that no one tried to put it in a software with realistic results, with results you can really work with. Why you can wonder why Wi-Fi heat maps are working, but we don't have the same for UHF signals. First of all, I would question that they are really working. But the second thing is that the wavelength of Wi-Fi is much smaller and the behavior is a little more predictable. Plus, there is such a big market for Wi-Fi heat maps and such a small market for a UHF heat map software that probably no company thought about developing it. But generally, I'd say it's not really something that you can really trust. Okay, I hope I answered all your questions. I hope you will have more questions. If so, please, you will receive a thank you email for attending this episode of a webinar, and there is a form that you can use to ask other questions, to get in touch with us, with me, kind of directly at any time. So please use it, and thank you for your time. I hope I will see you in a better shape, and we will finally see a little better the end of this crisis when next episode will take place in 2 weeks from now. Thank you very much, guys, and I hope I see you soon on the next webinar, but I hope much more to see you soon in person at some of our shows that we miss so much. Thank you very much, and stay healthy and stay safe. Bye.